we're going to talk about the periodic table and specifically the history, the regions of the periodic table, and some properties of elements and states of those elements on that periodic table. So first of all, leading up to the periodic table, the current periodic table that we have now had some predecessors and some previous work that allowed the creator of our current periodic table to do his work. It started out with the law of triads, which was basically saying that there were groups of three elements that had similar properties. That was improved upon when de Chancantois worked on that pronunciation. I don't think I quite hit it, but when he arranged the atoms by increasing atomic weight, and in groups of 7, we saw periodicity in groups of 7 where these atoms started to behave similarly every 7 atoms. And so his work was then, it was actually pretty strong, but he was a geologist, and how he published his work, it wasn't as useful to chemists as it was to geologists. So then Newlands came up with the law of octaves, which is based on eighths, which is more similar to what we have today. And finally, Meyer produced a table that was very similar to the current table, but his just wasn't produced in time. So who actually came up with this was Dmitry Mendeleev, and he put his atoms on the periodic table by increasing atomic number. That's really important, increasing atomic number, which is really the number of protons that an atom happens to have, and then also by families. So by putting these in increasing atomic number and then having the families where the properties were similar line up to each other, we have the periodic table that we have today. Now we can label the periodic table in terms of vertical arrangement, so going up and down. And if it's an up and down, it's called a group, a family, or a column. Or if we're talking horizontal, we would call it row, period, or series. And then this word period is where we get the periodic table. So we have a couple names that we need to know. You need to know that a family called group 1, so the first vertical arrangement is the alkali metals. Then we have the alkaline earth metals, that's group 2, again vertical. All the way over on the other side of the table, group 7, VII, would be the halogens. And finally the noble gases, which would be group 8. So we just talked about group 1, alkali metals, group 2, alkaline earth metals. Over on the right hand side, group 7, which would be the halogens, and group 8 would be the noble gases. But we can also talk about other large regions on the periodic table. We have the metals. So everything to the left of the stair-step line right here, these are all metals, even down at the bottom, the lanthanide and actinide series, except for hydrogen. Hydrogen is actually a non-metal. It just electronically behaves like group 1. Then we have the metalloids. Those are atoms that have two surfaces touching the stair-step line. Now, not all of the ones that have two surfaces are metalloids. We have boron, silicon, arsenic, tellurium. So start at boron, count 4 down, go left, antimony, germanium. Aluminum doesn't count, and then for us, we're not going to count polonium and astatine. And finally, we have nonmetals, which includes all those to the right of the stairs, and hydrogen. Then also know that these are sometimes called the rare earth metals down at the bottom, the lanthanide series and actinide series. Just depends on your resource that you're looking at. I wanted to show you a different table because this lanthanide and actinide series actually belongs right here. It's just that if we use this version of the periodic table, it doesn't fit very nicely on a sheet of paper. So what chemists did is they just took these elements right here and they moved them down to the bottom. And then we just know that this black line, in order to go from barium over to 71 here, we have to first follow this line and go through the lanthanide series. Or to go from radium over to 103, we have to first follow this line and go through the actinide series. So element properties, metals, first and foremost. Metals tend to, now this isn't all metals, and this is varying degrees of how good they are at doing this, but metals tend to be good conductors of heat and electricity. They are normally malleable, which means they can be hammered into thin sheets. I like to think of a hammer as a mallet, so I remember malleable is thin sheets. Ductile means they can be drawn into wires. Now, I think of heating ducts in the basement of my house, and heating ducts are long and drawn out tubing, which is a lot like a wire, and then lustrous, which means shiny. So those are properties of metals. And then we have nonmetals, which are the opposite. So if metals were good conductors, nonmetals are poor conductors of heat and electricity. They are not malleable, so a word for that would be brittle. If you were to hit it, it might just shatter or make a good powder. They're not ductile. We can't draw them into wires. And they're not normally shiny. They're dull in color and nature. Finally, the metalloids, or also known as the semimetals, these are a combination of metals and nonmetals. Now, which are they emphasizing is based on what side of the stair-step line they're on. So if you're on the left side of the stairs, in other words, on the metal side of the stairs, you're going to be more metallic. So germanium and antimony tend to have more of those metal characteristics, even though it's a combination of the two. And then on the right-hand side of the stairs, boron, silicon, arsenic, tellurium, they're more non-metallic in nature because they're on the non-metal side. And all these elements, they have natural states. So most elements are found as compounds. We don't find them as just elements. You can't dig a hole and get a whole stack of sodium, for example. Sodium is going to be stuck to another atom, and that's so that they become stable. Atoms want to be stable because that's just a more comfortable way for those atoms to exist. But we do find some atoms as just pure elements. So for example, noble gases, group 8, such as helium, neon, argon, etc., those are found as just atoms because they're already stable. They already have a full valence shell of electrons. And then the noble metals, gold, silver, platinum can be found all on their own. They can also be found compounded, but in general, we find specifically gold. If you've seen any of those TV shows about gold rush and stuff like that, they're always finding just pure gold. It's not compounded because it's pretty stable as it is. And then we can talk about diatomic molecules. So di means two, atom means atomic. So these are molecules, or also sometimes known as diatomic elements. These these 7, hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, fluorine, always come attached to another one of themselves. You do not find hydrogen as just one atom. It's going to be found stuck to itself as two hydrogen atoms, H2, O2, N2, CO2, Br2, I2, F2. So you can remember this mnemonic. It's called Hunkelbrief. Another way to remember these 7 is if you start at element 7, that's nitrogen, you draw a 7, and then you count 7. There are 7 of them if you also include hydrogen. So if you start at 7, that's nitrogen. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So nitrogen, oxygen, fluorine, that's your 7. And then fluorine, chlorine, bromide. And then hydrogen makes it 7. And then finally, some atoms like carbon, and there's other examples of this too, can come as multiple varieties. So carbon can make diamond, or can make graphite, or can make Buckminster fullerene. And for all these cases, you have different quantities of carbon atoms stuck to itself, but then the structure of that has different structure creating different properties, and those would be called allotropes. This is a picture of what Buckminster fullerene happens to look like. These are all carbon atoms just stuck to each other, and they make these little buckyballs is what they're sometimes called. So what you should have learned in this presentation is some of the history that led up to the periodic table. It wasn't just a unique discovery. It was a bunch of research all building into this table that we have today. The guy who came up with that was Mendeleev, and he did it based on increasing atomic number, that's important to recall, and then families, behaviors of properties in the same column that are similar properties. Moving forward to that, we talked about properties of these atoms, different regions of the periodic table, and some names of those families. Hope that helped.